We start a new topic in this course, and that is on clustering and classification. So, the classification is a task of assigning a known category or class to an object. For example, you take this image and you are asked to classify in this image that which are the regions which contains human and or which contains which and whether it is human or non-human. So, this is a classification task. So, suppose I have given this particular region of the image and I asked you to classify whether it contains human or not. And in this way, I can in this system I can give various patches from this images from this image, and we can ask to solve this problem. There could be other kinds of problems also, like detection of pedestrian in an image patch, recognition of an alphabet given a 2D pattern, assigning a pixel of an image to its foreground or background. So, these are different other classification problems, and in this way you can define infinitely many types of problems. So, this is the nature of a classification problem. Whereas, a clustering, it is the task of organizing objects into groups whose members are similar in some way. So, the cluster is a collection of objects which are similar to each other, but dissimilar to the objects belonging to other clusters. You can consider examples of some of the clustering as finding out regions of homogeneity in an image, and which means you are deriving segments. This is also a problem similar to clustering, or grouping of similar components. And example we can see here, suppose I have given an image of mushroom and in the background there is a humus substance, and we would like to cluster the similar pixels or similar regions in this case. So, one result could be in this form. Here you can see that there are primarily two regions or two types of clusters there shown by the green contours and red contours. Again, there are different regions of green contours and red contours which can be treated also as segments. So, what is the difference between class and cluster? A class is a well studied group of objects identified by their common properties or characteristics, whereas a cluster, it is a group with loosely defined similarity among the objects. It is potential to form a class. So, what are the motivations of clustering? I have given one example of its applications, like segmenting images. We will see different other motivations, like you can find representatives for homogeneous groups, and this would reduce your total data representations. You can represent data by a smaller set of representative samples bearing those characteristics of data. Then discovering natural groups or categories, that is also another motivation. So, that we can describe them by their unknown properties, and finding relevant groups. So, segmentation is one such example where we would try to draw our attention to relevant groups in the distributions or in the images. So, it is the major groups in the given context that we would like to identify, like segments of an image. Then detecting unusual data objects, so which are like outliers in the data. So, those are also can be detected using this kind of clustering techniques. So, in the context of our image and image processing, computer visions, also video processing. So, how clustering and classifications are placed in this particular processing of information. So, as you can see that it is a very high level processing of information. So, at the lower level from the images, we would like to derive certain representation of data in terms of feature extraction. So, it should pass through the process of preprocessing, feature extraction, and then you can get the represent the objects or images, image patches by feature descriptors or feature vectors, that we have discussed already in previous lectures, and we know different techniques of deriving the points of importance, relevance in an image, and then describing their neighborhoods, or also different patches or images we can describe by their corresponding feature vectors. These feature vectors, they are the representative of those corresponding class or groups or objects. They are used for the purpose of classification and clustering. So, and then you have to the task is that you have to assign them certain known or unknown groups, whatever. That means they should be similar. For clustering, groups are not well defined, as we mentioned. So, in the example with different colors, we are trying to represent those different kinds of classes or groups. So, we can see the approaches of clustering classification, which are essentially learning problems. Now, there are two approaches, supervised and unsupervised learning, when you consider as a learning problem. So, here we are learning about groups or categories in data, and when we say it is an unsupervised learning, then it learns in the absence of almost any prior knowledge of groups. Almost I told, because sometimes the number of groups, that information is provided. Now, this problem is like clustering. So, in clustering we used unsupervised learning, and in a supervised learning it exploits knowledge about the classification problem, such as example instances of classes. Say in this case, training samples with class labels are provided for solving this problem, and it finds features suitable for predicting classes. So, this problem, supervised learning, is also used in solving classification problem. Now, there are other variations in this learning framework. You have semi-supervised learning and reinforcement learning. Like in semi-supervised learning, it learns by making use of unlabeled data for training in conjunction with a small amount of labeled data. Usually, the sizes of unlabeled data, they are large, and labeled data, they are kept small. And in this case, this framework, this learning mechanism, it falls between unsupervised and supervised learning. In the reinforcement learning, it is learning by feedback from a teacher or a critic in the form of reward or punishment, yes or no, true or false, etc. So, we will be discussing now the methods of clustering techniques. We will first discuss methods of clustering techniques, and then we will discuss about the classification techniques. So, in clustering there are three major components. The first, it should have a distance measure, or which measures similarity between two data samples, and then there should be some criteria function to evaluate clusters, and then of course, the methodology, the algorithm by which you should compute, you should solve the problem. So, for defining similarity, different distances could be used, and some examples of distances we have already seen in various other applications in this particular course, also under various topics. Suppose the L1 norm, L2 norm, and a generalized LP norm could be used. And for criteria function to evaluate clusters, there are two particular properties which are looked for in having a good clustering solution. One thing is that there should be a good intra-cluster cohesion, which means the members of the clusters, they should have good homogeneity property. And one of the measures in this case could be sum of squares of error of deviations from that property, or there should be inter-cluster separations. That means groups are also well separated, well discriminated. About the clustering algorithms, in this particular lecture or in this course, we will be learning three different clustering algorithms. One is K-means, and then K-medioids, and mixture of Gaussians, Gaussian technique. But there could be various other approaches, like there could be hierarchical clustering techniques, graph based approaches, etc. We will be considering only these three in this course. Homogeneity and separation principles that we discussed when we are considering evaluation of cluster clustering, evaluation of clusters, those are derived by a technique. So, homogeneity, as I mentioned, it is elements within a cluster which should be close to each other, and for example, you can compute the average distance of these elements from the cluster center. So, if this distance is small, then the cluster is good, it preserves the homogeneity, it has good homogeneity property. Whereas, the separation property in clusters are the elements in different clusters, they should be farther apart from each other. So, in this case, you may compute average distance of pairs of cluster centers, and those centers should be should be placed apart. They should, so this distance should be large for having a good separation property. There could be several choices of clustering or partitioning. So, it's a non-trivial partitioning problem in that sense. Suppose I give you this data distribution, it is a two-dimensional data points which are shown by these circles, and locations of the data are shown in as a two-dimensional coordinate space. So, these are the elements. So, one kind of partitioning could be like this, and the other kind of partitioning could be like this. Now, by considering the two properties of homogeneity and separation, the first one is a bad clustering example, whereas the second one is a good clustering example. So, the first technique that I will be discussing here, it is called K-means clustering technique, and in this case the problem is that if I give you n data points, then you need to compute k partitions, though partitions are actually clusters, so that it minimizes the sum of square of distances between a data point and the center of its respective partition or cluster. So, this is essentially an optimization problem, where you can consider this mathematical formulation of the optimization function. So, you see that optimization function which you require to minimize, this is actually sum of square of deviations or distances from the mean of a partition, which is denoted here by Ck, and to the points which are included in that partition. And if, since there are k partitions, you perform this job k times. I mean, you have summing all those components of k partitions. Now, this problem is an NP complete problem, provided k is greater than 1, because if there is k, it is just the center of the cluster. If you compute the center of the data, that itself will give you the solution. So, the algorithm for K-means clustering, it is a very famous algorithm, and which is known as the Lloyd algorithm by the name of the inventor of this algorithm. So, it is given as k initial centers, assigns given k, first you consider randomly, you can choose k initial centers, and then you can, based on that, you can partition them by assigning the nearest center to a particular point. So, the cluster of the by assigning that cluster whose center is nearest to a point. So, it is the closest among them, and then we can update the centers once again the partitions. So, centers gets updated, because once you get the partition and you can compute that center, that would be definitely different from what you had earlier, and you can iterate these two steps till the centers do not change their positions. A very simple approach, but very effective. So, what it is trying to do? It is trying to minimize the energy function defined by the sum of divergence or say of each cluster from its center. It is the error function what I discussed in the previous slide. So, this is this function what you are trying to minimize. But this method, the convergence not guaranteed, but works well in practice, and it may get stuck at local minima. That is another problem. So, let me show you figuratively how this approach works, the essence of this computation. So, we consider once again the distribution of the points in a two-dimensional space, and points are shown by circles, their locations are shown the corresponding center of the circles. So, what we can do, that we can choose initial cluster centers. For example, say these are the two initial hypothesized as two cluster centers. Then what you should do, you have to now compute the partitions, which means we have to consider the points which are closer to a particular cluster center. So, the corresponding cluster label should be given to those points. So, here the labels are shown by colors for the visual purpose of visualization. So, I will show the labeling by color. So, you can see these are the set of points which are found to be close to the cluster shown by the color pink and the other one by the color green. So, now you have it two partitions once again based on those centers, and now you should again update this center. So, you can update these centers, which means now the centers they should move inward because of the configuration here, and you get this is the updated positions. Again you perform the partitioning with these two new positions. So, compute new partitions with updated centers. So, now you will find that these are the set of points which are being clustered, which are closer to the corresponding centers, and they are shown by their colors. So, you repeat these operations. You update centers and move the cluster centers, updates and move the cluster centers. Once again, you perform the partitions, and you will find that you get a new partitions here, and you should update the centers, and it will be moved further. And in this way, you will find that after few iterations, there is no change or a very little change in cluster centers, and then you should stop. So, this is how the K-means algorithm works. There is a more conservative approach of this particular algorithm, because Lloyd algorithm is first algorithm, but it is not necessarily causing better convergence. So, a more conservative approach is to move one data point at a time, provided overall cost gets reduced. So, it is a greedy approach, and what it does in the principle of this approach is that it chooses the transfer of a data point from a class I to another class j, which causes the best cost reduction, that means the maximal cost reduction at that step. So, we can describe these computations in an algorithmic steps. So, you select an arbitrary partition P into K clusters, like the K-means clustering algorithm, and you should repeat the steps till convergence of this cost. So, let us consider we keep track that what is the reduction at this step. If there is no reduction for some iterations, then we should not, after some iterations, then we can stop. So, initially it is initialized with 0, and then for every cluster C and for every element which is not in C, you perform these operations. We perform the reduction, that is the difference between cost of partitioning of P, which was there earlier before the transfer, and what is the cost after the transfer. That means, you have recomputed once again the centers and partitions. Now, this can be done efficiently by simply considering the clusters which are affected by this transfer, by recomputing their means. Rest other partitions, levels of the rest other assignment remains same, and then you can quickly compute this cost. So, if this is there is a reduction, and if this reduction is greater than the maximum reduction, then first thing, if there is a reduction, then you should move update C and the cluster containing I. So, which means at every iteration we are considering for all elements what is the reduction of cost, and choose that transfer which is the maximum, and at that iteration only that transfer is used, and go on doing this. So, it is a very slow process. It is not so fast of Lloyd's algorithm, but its convergence is better, which means, as I mentioned, that K-means algorithm may get stuck at local minima. Similarly, this algorithm also, it is not guaranteed that it will get a global minima, but it should get a better local minima by this process. So, that was about K-means clustering. A variation of K-means clustering is called K-medoids clustering. So, let us understand what is defined by a medoid. A medoid is the representative element of a set of data point with minimal average dissimilarity with the other data points in the set. You consider the data points they are all vectors here. So, it is nothing but the median vector, what is defined conventionally in signal processing community. So, this definition mathematically can be represented in this way, that given a set X, its midpoint is given by this is what you compute the average of the distances from that point to other points, and consider that element in that set which has the minimum such distance. So, that is how the midpoint is defined. The advantage here is that it is like median of a set what we get. So, in the median of a set, it is one of the elements of the set. Similarly, midpoint is also one of the member of this data set. So, the cost to be minimized in k midpoints clustering, it is almost structure is same. Instead of the cluster means, now we have replaced means by the cluster midpoints in the expression. So, you can see this is the almost similar expression, where these are the midpoints of cluster K. So, K midpoints clustering could be almost similar to K means clustering. As you can see that this is the same algorithm, except the fact that instead of updating cluster centers or means, we are updating midpoint. So, iterate above 2 steps till the midpoints do not change their positions. So, the corresponding changes in this algorithm, they are highlighted by this red color. But the problem is that this updating of midpoint is very computationally expensive. It is not so simple like updating centers. As you have seen, for every cluster you have to compute the corresponding median vector by solving that problem. So, we need to we can have some other variations to make this computation faster. One of the approach is that we can consider computing midpoint of only two clusters instead of all. So, randomly choose an element of a different cluster and swap with the midpoint element of one of the clusters, and update the midpoints. If the cost decreases, then only you accept the swap, and then you continue these operations till it converges. So, this algorithm is also known as partitioning around midpoints or PAM. The last technique of the clustering methods which we will be discussing in this particular subject, that is use of mixture of Gaussians, and by analyzing the probability density functions of the data in terms of representing it as a mixture of Gaussians. At the outset, we can consider some similarities with the K-means clustering technique. Say you consider a cluster center is augmented by a covariance matrix. It is not say center is the mean of the data, but let us consider also you are using its covariance matrix, and for every at every iterations you are updating corresponding means and covariance matrices, and the distance function could be used like a Mahalanobis distance function. So, this is the example, this is the expression for Mahalanobis distance function. As you can see, it takes into consideration of the covariance matrix also, not only the mean. And so, this is a cluster center and this is a covariance matrix. So, you can apply like K-means algorithms, but of course, this is not the technique of mixture of Gaussians, but this has some similarity. What we can do instead, we can refine it by computing probabilities of belongingness to a cluster. So, instead of crisply defining the membership of a cluster for every element at every iteration, we maintain a probability of belongingness and continue doing these things till we get a good good probability density functions which defines the which describes the corresponding distribution of data, consistently describes it. So, what is this? This parametric probability density function is described by mixture of Gaussian distribution. So, this is the description here. You can see that probability density function of a data point x is given as a mixture of normal distributions. So, weighted sum of normal distributions, where weights are given by the parameters pi k, and each normal distribution has its own center and covariance matrix that means they are denoted by mu k and sigma k. Just for the completeness, I am also providing you the expression for normal distribution in multidimensional space. And the mixing coefficients are here, they are called this pi k. So, there is an algorithm which is known as expectation maximization algorithm, and by which you can estimate these probability density functions and get those mixtures, get those Gaussian distributions, and each Gaussian distribution component is representing like a cluster here, and so elements which have higher probability due to that Gaussian mixture distribution, those elements are assigned to those clusters. So, that is the process. So, what we can do, we can start with an initial set of these parameters. So, any arbitrary parameters you can choose, and in the expectation stage, what we do, we recompute the probabilities or likelihood of x of the data to a particular kth Gaussian cluster. So, for each cluster center we compute its likelihood, which means I have to compute simply the probability given that distribution, and which has to be multiplied by. So, this is the likelihood which we need to compute, and you can see that we are computing the probability of corresponding probability of xi belonging to this distribution. This is given by this probability density function. It needs to be multiplied by the mixture coefficients phi k, and zi is the normalizing coefficients, because you are considering k classes. So, for all classes, I mean with number of classes, for each classes you are computing zi k for xi pixel, ith pixel. So, in this case this x is should be indexed by I. So, we are considering the ith pixels, and this is how we compute the likelihood. And then we assign this pixel, ith pixel or xi, we can assign it to the mth cluster whose likelihood is maximum. However, no, this assignment is an optional step. It should not be taken at this at every iteration. Only at the final stage, when you computed all the probabilities of likelihoods of every points, then only you assign the cluster which has the maximum likelihood. And the maximization, so this is the expectation stage. So, you are computing the likelihoods, and from there you get a redistribution of redistribution of data. In the maximization stage, once again with this likelihood of data, you re-estimate the parameters of the Gaussian distribution. So, you continue this process. So, this re-estimation process, let me explain more in an elaborated way. So, as we have seen that we can compute the likelihood of the data, this is the expression by computing the probability using the probability density function for kth Gaussian distribution in the kth Gaussian component, multiplying with the corresponding mixture coefficients, and then normalizing with respect to all the classes or components, clusters. So, if I have this likelihood, we can consider the strength, it is as if it is representing the number of points in a cluster. So, it is not a discrete number, as you can see, it is sum of probabilities of all pixels, whose sum of likelihoods of all pixels, which is not an integer, but it is an estimate of the number. It is giving a probable estimate of the number. So, if the likelihood is 1 and 0, then you get integer numbers, but in this case we will get an estimate of that number, and this is how it is defined. It is the expected number of pixels in class K, which has a fractional component also here in this framework. So, now you compute the mean of the distributions, you compute the mean of the cluster K by considering the corresponding say likelihoods as the weights for a particular data point. So, it is the weighted mean of the data points belonging to that cluster. So, the belongingness is defined by likelihood. That is how you get the mean of the cluster. In the same way, you get the covariance matrix of the cluster. So, this is how the covariance matrix is also computed. So, now you see that from here you get at least two sets of parameters of means and covariances, and finally, the mixture coefficients that pi k, those are also found as a fraction of total n. Here n is the total number of pixels in the image. So, n k by n, or total number of elements in the data points, it is not only image, it is the data points. So, n k by n will give you the corresponding probability of a, or prior probability of a class k. So, it is acting like a mixture coefficients. So, you iterate this process, and through iterations you can converge, you can, after convergence, as I mentioned, then you assign the highest, assign the corresponding cluster which is represented by a corresponding Gaussian component to a pixel which has the highest likelihood to that component. So, this is how the Gaussian mixture of Gaussian method could be used for clustering. So, let me stop here, and we will continue our discussion on classification in the next lectures. Thank you very much for your attention.